Good morning, everyone. I'm Naskar from Carbon and Composites Group in Material Science Division, as well as from Carbon Fiber and Technology Facility. So before I start on these details of this technology, I wanted to mention that we are working on carbon fibers and composites for more than a decade here in this lab. And in fact, during this period, we developed different technologies that are, some of those are already commercialized. And the most important thing probably happened over last couple of years, and some of you were engaged with us on commercialization of textile grade carbon precursor for manufacturing of carbon fibers. So that's the baseline, whatever the knowledge base established there. And during this period, what we were doing, we were focusing on manufacturing of carbon fiber using whatever precursor that are available or that are industrially made for commercial purpose. So that gave us an opportunity to look at, can we really go back and see if we can improve the precursor? We were not doing research on precursor development historically, but seeing the success over last few years, so we redirected the focus. In this particular case, we are trying to understand or apply whatever the knowledge base we have developed utilizing some of the tools. I'll not go through the details of this. Some of the tools that are available here in this lab, we used scattering probes at PNMS. In fact, we did some of the neutron scattering work also here. So based on that, we developed some understanding, and also we are doing fluid flow and rheological measurements of these solution before manufacturing the precursor fiber. And based on that, we conceived some idea and we demonstrated the proof of concept here. And with that, I'll start. So the title of this one, Improving Carbon Fiber Production, High Quality Carbon Fiber at Significantly Reduced Price. So overall, why we are doing this? Again, it has to be economic. So that's why significantly reduced price is mentioned there. But quality of the fiber, can we really improve the performance of this fiber? That is the goal. So if we look at, I mentioned about textile grade carbon precursor, it is all of these precursors that I'll talk about today, all these are polyacrylonitrile based, PAN based precursor. So I mentioned earlier that textile grade PAN material has been converted to carbon fiber earlier. What do we see in that textile grade PAN precursor? So this is an XRD pattern of carbon fiber. So you do have fiber, pass it through oxidation oven, carbonization oven, and make the fiber. You measure the mechanical properties of this fiber. If it is good, then we say it is a good fiber, and then we use it for composite application. Now, what is the features in this fiber that make it a good fiber? That's what we are trying to address. So if we look at the X-ray diffraction pattern of these in the background image, that top one is a commercial fiber and bottom one is a textile PAN based fiber. The two lobe up and below in the, so the white line that is going there, that was the beam stopper. That's how the X-ray goes through, and fiber is staying here, and that's the image plate that is collecting the image. Now those two are the lobes up and below are the 002, that is the graphite diffraction peak there, and the nature of that peak, how broad it is, that tells us what is the orientation factor in the carbon fiber. Now orientation factor in the carbon fiber is critical. That's how you improve the mechanical properties, and you might have heard that in carbon fiber manufacturing, we always talk about stretching, stretching, and stretching. So if you can orient or align the carbon materials along the fiber axis, then your performance goes up. Another way of doing it is do high temperature treatment. Still, in this method, whatever fibers we have made, if you look at the misorientation angle. So misorientation angle means how broadly these fibers, so this is my fiber axis, crystals should be oriented. If they're all oriented, then misorientation angle is 0. So that will not be the case, but there is some crystals are, I mean, not necessarily perpendicular, but in a certain angle, and that can be in both sides. So So we take that angle, that cone, that is the misorientation angle. Now, misorientation angle in this case is really very broad for textile-based carbon fiber. And that is a challenge. And that's why you see some variation in the carbon fiber properties. The misorientation angle in this case is 42 degrees. Can we reduce that angle and improve the performance? That is our goal. But that would depend on the drawdown ratio of the precursor fiber that we use to make the fiber. Now let us look at, I'll come back to this slide again. Let us look at how the fibers are made. This is a simplified version. I know in industry there would be a series of coagulation bath, second coagulation bath, third coagulation bath, washing bath. So maybe a series of coagulation baths would be there. But what is happening here, so this doesn't work on the screen, right? Pointer?
It works on the side.
Okay. So you have that syringe through which the jet, the green colored jet with velocity Vs is coming into the solid coagulation bath. And then the polymer is in a solution, that is a polymeric solution we are talking about. It comes into the coagulation bath, and during coagulation bath, it precipitates. Now, whenever it precipitates, we want to pull it along the fiber movement direction. We cannot pull it too much because the fiber is weak at that stage. Now, we are trying to understand how we can pull it better, how we can increase its elongational viscosity. That is the, again, entire theme of this particular research. And if we can increase the elongational viscosity, that means tolerance to stretch or extensibility, then we can increase the VR, rotation speed, in that. So if we can increase the rotation speed, so using existing equipment, you can increase the production throughput. Not only that, when you are increasing production throughput, your fiber is also getting more aligned during the fiber axis direction. And that if you have higher V1, then you can gradually increase the speed of production in every stage. Now I'm coming back to this. So what can I do? Is there any feasible path to induce higher degree of orientation during this fiber manufacturing? Or can we upgrade this existing textile-PAN by this process without significant capital investment? So that's our goal. So what we have done, we prepared a polyacrylonitrile composition. So our precursor material, suppose you are a textile manufacturer, or I am a manufacturer. So I have my existing plant with standard polymerization and fiber spinning line. I wouldn't interrupt that process, but can I really incorporate something into the system that would increase the extensibility of the fiber so that you can increase the throughput of the material through the spinning process, as well as you can increase the stretchability or the speed of the material. So that's what we wanted to do, and what we have accomplished, we first made a composition and a process that enhances fiber spinnability and extensibility. So we made a composition using standard textile precursor, and we added a rheology modifier. So when you add a rheology modifier, rheology means study of deformation of fluid. When you are adding that modifier, you are increasing the material's extensibility significantly. So let us see what is the characteristics of rheology modifier. So obviously, I didn't show here all the infrared as well as NMR spectra to identify the composition immediately. We can talk about that if you want later on. Nevertheless, I wanted to mention here that the rheology modifier marked in blue color has a significantly higher molecular weight. So this is something that we synthesized in our lab. It's also a carbon precursor. It is PAN, polyacrylonitrile, and it has a controlled polydispersity index. Slightly higher, but more or less okay, 1.8 to 1.9. And we have compared it with commodity precursor as well as some example carbon precursor that exist in our lab. And you can see that it is slightly higher in molecular weight, but more or less okay. So this is a size explosion chromatography data using refractive index detector, RI detector, and elution volume. So just wanted to say that this is a type of PAN precursor that we have synthesized, which is nothing but a PAN with certain molecular characteristics. So when we use this PAN precursor in existing textile PAN solution, so standard textile precursor, so whatever the material is making, and I am adding this separately rheology modifier, another PAN into the system, and then let us see what happens to the material's flow characteristics. So the blue curve, it's a complex viscosity versus frequency. So when you are increasing the shear, the viscosity of the PAN is dropping. And look at the PAN's viscosity. The blue curve viscosity is several order magnitude higher than the modifier that we prepared. And look at the shear thinning behavior. As you are increasing the frequency, the material is thinning down dramatically. But that's common in any polymer solution. Polymers, whenever you are increasing frequency or you are increasing shear rate, they will disentangle and they will slide past one another and viscosity will drop. So it looks like the blue curve would be probably a good one. But I'll show you the next data later on. We will discuss about that. But let us look at, before going to the next slide, let us look at what we are seeing in case of the orange colored rheology profile, which is the modifier one that I added. It remains more or less steady. It is relaxed molecule. It doesn't decline because there is not much entanglement. It is a relaxed molecule in the solution. That's why it more or less, it is almost like frequency independent. It is in relaxation plateau region. And when you are adding a fraction of that, like very little fraction of that material into the blue curve solution, then the green curve comes and you see how much we could modify the flow characteristics of this material. But now this is in terms of viscosity versus angular frequency data. Let us look at the extensibility data, like storage modulus, why this material will tolerate better speed that I was proposing earlier. So look at the blue curve again. It is PAN solution, its modulus versus frequency. Modulus means resistance to deformation or stiffness, right? So that gel, when we prepared and we are trying to flow, if you try to flow faster, if you are increasing the frequency, the modulus is not increasing. So that means that the PAN, when PAN molecule is in a solution, all these dipoles are interacting with each other and it is almost behaving like a cross-linked gel. No matter whether it is a PAN, whether it is textile PAN, or it is specialty acrylic PAN, it will behave like a gel. And where from this gel behavior is coming, that's because of their dipole-dipole interaction. Now, that's why if you try to pull that material, it will not show resistance. Its resistance to flow is not increasing. On the other hand, look at our modifier solution. It has lower viscosity. In previous slide you saw. So that means you can increase the throughput. Viscosity means low viscosity, so you can push the material through your spinner rate at higher rate. And not only that, whenever you are increasing the speed, so you are pulling the fiber at faster rate, and when you are pulling the fiber, its resistance to flow is increasing. That means the material will not break anymore. Its stiffness is increasing. As the stiffness is increasing, you can spin the material at a faster rate. So that's what exactly we have accomplished. And we have started, whenever you will see go through our lab, you will see we are spinning the fiber there. I didn't show any spool picture or their conversion data. I'll now switch on to conversion later on. But you will see that we have established a spinning lab and we are producing fiber from all these compositions that I mentioned, including standard precursor. We are also synthesizing all these material in textile equivalent precursor as well as modifier, and we are producing the fiber. Now let me come to a bigger challenge now. I made the fiber, right? Precursor fiber with higher extensibility. So obviously we see based on this data, these materials will have a higher degree of orientation. So simply, since it has a higher degree of orientation, it will have a higher mechanical properties. So what happens to my conversion characteristics? How does it influence my conversion characteristics? Conversion characteristics means when I'm oxidizing this fiber and then carbonizing subsequently, how does it compare with standard oxidation parameters? Historically, we have learned that if you have a fiber with higher degree of orientation, when you have stretched too much, it will show you slower kinetic parameter. It will not tend to oxidize that fast. So we are creating problem for our future, right? We are making oriented fiber because of higher throughput. We made good fiber, stronger fiber. It can tolerate higher stretch for our subsequent higher performance goal, but my kinetic parameters are slowed down. And that's because of high alignment of that, and during oxidation, molecule need to relax and shrink. So it has resistance to shrink, and that's why the kinetic parameters are slower. Now, how shall I address that? I have to have a good conversion recipe for these precursors. So higher degree of orientation is really good for your performance of the carbon fibers, but slower kinetic parameter is detrimental for manufacturing throughput. Now imagine the technology that we have developed earlier, where we tried to make textile-based carbon fiber at high throughput rate. Now all those, whether it is textile-PAN or other PAN, specialty acrylic PAN, all those, I mentioned about that, that is our baseline, whatever knowledge base we know, all those methodologies would be applicable for this material too. No matter whether you have textile or specialty acrylic fiber, if you have higher orientation factor, your kinetics will be slower. So how shall we address that? So we devised an approach that addresses slower kinetic parameter for textile or any other precursor for converting it to infusible material. So let us look at, this is differential scanning calorimetry data. Basically, when you are heating this fiber in air, so some heat is evolved because of the exothermic reaction. So at what temperature the heat evolution starts, that's what we are monitoring. Now look at this textile precursor, the blue curve, which onset is somewhere around 250 degrees Celsius, then sharp rise in exotherm. And that's why textile-based conversion is tricky. At what temperature you would oxidize and carbonize, because a lot of heat, whenever it evolves, then it may melt the fiber or break the fiber toe. So what we have done, we developed a recipe for these precursor or any other precursors where you can treat the fiber on its surface, then it would induce the oxidation rate slightly better. And I don't want to perturb their kinetic parameter too much. Then I have to redesign my oxidation oven or other thing. Then probably I'll make not necessarily a textile precursor, I'm going to make a specialty acrylic fiber. So I have to be careful. Then it will not be a cost economic anyway. So what we have done now, look at the green curve, we have done an induced reaction somewhere around 200 degrees Celsius, not rapid, but slight, satellite peak type, exothermic peak, you can see that. So it is showing some degree of reaction there. So that's what we want. We want it to start kicking in the reaction at early stage. That is good, but you don't want it to be so vigorously evolving heat so that it will melt or shrink too much. So that's what we have exactly devised. And then let us see, we formulated different composition and we validated with that. And now I would like to mention that these technologies, that whatever we have developed, it doesn't necessarily need a particular co-monomer. As long as you have a certain constant mole percent of polyacrylonitrile or acrylonitrile mole percent, it should work, and it works. So if you have a different co-monomer, whether it is, all those are esters, whether it is acrylate or acetate-based co-monomer, it doesn't matter. It works because it affects the acrylonitrile fraction and it does the reaction. And in this case, we can move it very fast, but that would create problem for us later on, because before orienting the fiber during oxidation, it would start cross-linking, and that would create a crappy carbon fiber. So we don't want that. So we did it slight modification, and we tried to move the exothermic reaction towards lower temperature. So that's how. Now, is this heat affecting or air-based oxidation, cross-linking reaction. It is oxidation. How do we know that? So we did the same materials run in nitrogen in inert atmosphere, and you see in inert atmosphere only the heat affects, and all those are not much. You can see that it is almost like 300 degrees Celsius the peak is, so peak is shifted. So not necessarily the heat. Air and heat both are working there. So it is oxidation reaction, and that does this pre-stabilization, and which will accelerate further and perhaps will increase the throughput of carbon fiber manufacturing. Now, is this applicable to any other precursors? Yes. As long as it sees a PAN molecule, whether you have a textile-based PAN or specialty acrylic PAN, these chemistries are applicable. And in fact, this is a spool that, of course, very tiny spool, monofilament we produced in our lab. This was done by melt spinning. And when we have done that, melt spinning of polyacrylonitrile, and we applied that, and we produced carbon fibers that meets the lower target. Of course, vehicle technology's target is very low. Vehicle technology's office of EERE, 250 KSI, 25 MSI type performance. But we can make that kind of precursor, or that kind of carbon fiber from these modified PAN precursors. In these cases, however, we did not use any rheology modifier that I mentioned earlier. So in summary, whatever I have presented, it has two components. One is, if I am a textile PAN manufacturer, how can I enhance my manufacturing throughput and improve the quality of the fiber? Now, drawdown ratio in the textile PAN manufacturing, precursor spinning operation, varies because of large material, because large tow material you are processing there, and it is going through, not necessarily all filaments are experiencing same thing. So can we normalize that by increasing the pull rate or the speed of the fiber? Then it would normalize better. So that is one aspect. So we are saying that we can modify the composition without interrupting the textile manufacturing process, modify the drop-in replacement of some portion of the textile PAN. It would still be 20% or whatever the percentage solid content that you are processing for manufacturing of this precursor. And then another component is, it is optional. If it can get converted to carbon fiber without any problem, that is good. But if not, because of very high degree of orientation, that's what we have experienced, that high degree of orientation retards the oxidation kinetics. So we have devised option for that. With that, I'd like to summarize that we have successfully demonstrated and developed an approach to induce better precursor from traditional textiles, and it can be any other precursor too, not necessarily textile-based PAN, using slightly modified approach during fiber spinning operation. So this modified approach is again composition and the modifier that we have synthesized in our lab. Higher degree of orientation causes retarded conversion kinetics with textile precursors. We agree that textile is as such, it doesn't have the axillary and functional group, that's why it is retarded. So we have learned how to address that. And this approach that we have mentioned, that modification, inline modification, so we will apply some sort of finish solution to the fiber, that it would kick in some early stage reaction, and then it would be helping you to stabilize it quickly. And this method is applicable for any sort of PAN. I would like to acknowledge TIP, Technology Innovation Program, that funded this project, and that's how we could develop it. And of course, my colleagues in Carbon and Composites Group, as well as Carbon Fiber Technologies Facility. Thank you all for your attention. Any questions, please?
So, Ahmed, you described a second step to modify the PAN prior to carbonization. Can that be applied to any textile PAN, or is it limited to your?
No, it can be any textile PAN. I would not dare to do that with specialty acrylic fiber because it has already some accelerant functional group. It would be vigorous oxidation reaction, but any PAN-based chemistry would do that. Gary.
Have you envisioned yet what the process equipment might look like for the modification and the spinner part of the
It is same exact whatever equipment you have, it would work. Only thing you may need. So I don't know whatever the textile manufacturers is doing there during the polymerization. I'm guessing that textile manufacturers will not precipitate their polymer. Whatever they're producing in solution, they will feed it through spinneret without precipitation of the polymer or dissolving that again. So my vision is, so when it is polymerized and when it is going to spinneret through manifold or somewhere in between, we have to make a stopgap storage tank where you are dropping in and creating this gel. And basically, we are inducing, we are incorporating another PAN which reduces the interaction between the PAN and makes. Imagine you have spaghetti, right? All those noodles are entangled and you are trying to pull it. So one end, so it will all be entangled together. At faster rate, if you are trying to, and imagine you have reduced the interaction or entanglement between that, it would come very easily and get aligned. So that's what we are exactly applying. So what you would do, the tank from which, the polymerization tank from which the solution is coming, that would still come. I would not interrupt there. And in between the manifold where from the spinneret, all the liquid is going or dope is going through, in between, I'll inject this modifier solution, and it doesn't require that much. And you don't have to prepare too high concentration, too low concentration either. You can make a concentrated solution and adjust this, it can get mixed up there. What else modification you may have to do when you are injecting this solution? Perhaps you have to have a starter to a mixer region. Not necessarily high temperature, but mixture. To homogenize that. That's all. I mean, I personally would not prefer to recommend anything that would cause a lot more changes in the manufacturing line.
Thank you.
Thank you, Gary.
So I understand sometimes with the precursor will start with 5 pre-stress before you're going to develop. Do you see your technology as completely replacing that, or having some benefit in using that process?
No, so there is an advantage of stretching during oxidation process. I don't want to eliminate that part. But let us think about the precursor characteristics. Just compare precursor characteristics between textile and specialty acrylic fiber. Specialty acrylic fiber, that whether it is Cytec, Toray, or Hexel, all these guys, they manufacture. Those precursors have drawdown ratio of more than 15. Drawdown ratio means how much it is pulled, right? From spinneret to winder, the velocity ratio, that's they call it. So it was stretched extensively. So that's why the drawdown ratio is 15 or higher. It can go up to 30. Now, what is textile drawdown ratio? Hardly 3. So, and that's why we do a lot more stretching during that operation. Yes, that's a good point. That if we are comparing the textile conversion process that we developed at CFTF a couple of years ago, there during the conversion operation we waste a lot of real estate there during doing stretching only, not much oxidation going on. If I have pre-stretched material, and that can help there. But I would not completely eliminate the need of stretching. There is certain requirement for stretching. Why that is needed? Because imagine a fiber is going through your heated chamber at high temperature, 200 degrees Celsius or whatever the temperature is, what it would do. Even if you have oriented fiber and if you have not restricted, they will relax. You will lose all this orientation, right? So to avoid that loss of orientation, and if you have a pre-stretched already, the shrinkage force will be tremendous. So you do not want to do complete elimination of stretching. You do not want to make textile from 3 drawdown ratio to 15. I wouldn't target that. So I'm thinking about somewhere in between. Can I get somewhere 5 to 7? And there is some advantage of using drawing during the oxidation process. I don't want to eliminate that advantage either. So somewhere, so hopefully, I'm optimistic that whenever you upgrade this material to drawdown ratio 5 or 7, 5 to 7 range, and you apply that material at higher throughput, your production rate will increase significantly. So that's the long-term goal, but I didn't want to touch that during this discussion without substantial data.